Now I will present you a dynamic partitioning method to solve the vehicle bridge interaction problem. It's also another paper of ours which we recently published in the Computers and Structures journal. And this illustrates an algorithm that partitions the vehicle and bridge systems, which means that it solves the vehicle and bridge systems separately, and also uses dynamic Lagrange multipliers. This is an approach that aims to ensure the stability during the time integration. So in this presentation, I will show you some main features of current numerical algorithms to solve the vehicle bridge interaction problem. Then the main premise on which the partitioning of the vehicle bridge system is based, and also how we formulate the problem via dynamic Lagrange multipliers. And finally, some numerical applications to show the applicability and also the performance of the dynamic partitioning method. So in general, the numerical algorithms to solve the vehicle bridge interaction problem, or in short VBI, typically rely on a solution of differential algebraic equations. Differential algebraic equations consist of the differential algebraic equations of the equations of motion of the vehicle and the bridge, and the algebraic equations of the constraints between them. More specifically, when the constraints are expressed on the displacement level, then we have an index 3 system of differential algebraic equations, which are known to encounter scaling problems, which require the adoption of a numerically dissipative algorithm. On the other hand, when differentiating the constraints, the index of differential algebraic equations can reduce to index 1 or index 2. In this case, some numerical drifts, some numerical instabilities may appear, which require the adoption of a stabilization technique such as the Baumgarten stabilization method. An alternative approach which avoids the difficulties of differential algebraic equations is the solution of the system as a set of exclusively ordinary differential equations with a minimum number of degrees of freedom. This is achieved by eliminating both Lagrange multipliers of the constraints and redundant degrees of freedom. In this case, the solution of the system reduces to the solution of an unconstrained system, which is always stable. However, the solution of a system with a minimum number of degrees of freedom can be impractical for large vehicle bridge systems with a large number of constraints. To this end, Natiavas and Parskevopoulos propose an alternative approach, which solves the system of exclusively second-order differential equations, but preserves both Lagrange multipliers and redundant degrees of freedom. To do so, this approach introduces dynamic Lagrange multipliers, which are position-like variables, which can be differentiated in time. This is different compared to classic Lagrange multipliers approach, which merely adopts static Lagrange multipliers. In addition, the constraint equations are formulated as second-order ordinary differential equations, which include the motion constraint G and its differentiations in time. On the other hand, classic Lagrange multipliers consider a constraint equation, which is solely an algebraic equation, either on the displacement or velocity or acceleration level. This system of equations solves the system of exclusively second-order ordinary differential equations, which avoid the instabilities and the difficulties which are associated with differential algebraic equations. In addition, the constraint coefficients of the constraint equations and Lagrange multipliers offer a natural scaling of the constraints. Lastly, this approach is appropriate for large constrained mechanical systems. So motivated by the limitation of existing algorithms to solve the vehicle bridge interaction problem, and with the aid of algorithms that can solve consistently a set of solely ordinary differential equations, we developed an algorithm that solves the VBI problem both accurately and efficiently. The proposed algorithm is based on two approaches. First, we partition the coupled vehicle bridge interaction system, and then we apply dynamic Lagrange multipliers, similarly to the approach that I just presented. So more specifically, to partition the vehicle bridge interaction system, we introduce a system of auxiliary contact bodies. These auxiliary contact bodies separate the vehicle and bridge subsystems. At the same time, these auxiliary contact bodies ensure the compatibility of the system at its time. More specifically, we introduce these auxiliary contact bodies, which allow the assignment of two sets of Lagrange multipliers. one between the vehicle and the auxiliary contact bodies, and one between the bodies and the bridge. Each one of the vehicle and bridge subsystems is assigned its own Lagrange multiplier, thus can be solved independently of the other. Similarly, the kinematic constraints are formulated between adjacent systems. Thus, the intermediate auxiliary contact bodies separate the vehicle and bridge subsystems, but at the same time ensure compatibility. This is the main premise at which the algorithm is based, and following, I will also show you specifically the equations that describe the problem. So now focusing a bit on the auxiliary contact bodies, those are fixitious bodies, which are essentially duplicates of the vehicle's wheels. That means that they have their own degrees of freedom, which are the same as that of the wheels, and their inertial properties are proportional to those of the wheels. The inertia properties specifically result via an allocation coefficient alpha. This allocation coefficient allocates the physical mass of the wheels between the mass of the auxiliary contact bodies and the mass of the wheels that is considered in the analysis. This coefficient should obtain values between 0 and 1, so that the mass of the auxiliary contact bodies does not become negative, and also the actual mass of the system is preserved. In other words, the sum of the mass of the bodies and the mass of the wheels used in the analysis should be equal to the physical mass of the wheels. So now the partitioning of the coupled system and the definition of the properties of the bodies follows the definition of the equation of motion and the constraint equations. So going back to the previous system, the equation of motion of the vehicle includes solely the dynamic Lagrange multipliers between the vehicle and the auxiliary contact bodies. Similarly, the equation of motion of the bridge only includes the dynamic Lagrange multipliers between the bodies and the bridge. The main difference compared to the classic Lagrange multipliers, as I also said in the introduction, is that we have dynamic Lagrange multipliers instead of merely static Lagrange multipliers. Then the coefficients of the dynamic Lagrange multipliers is described analytically in the cited study of Natsiavas and Paraskevopoulos. Another difference compared to classic Lagrange multipliers is that in this case we also have the equation of motion of the auxiliary contact bodies. This equation of motion includes the Lagrange multipliers of both vehicle and bridge and ensures the compatibility between the two subsystems. Lastly, the constraint equations between adjacent subsystems are also described as second-order ordinary differential equations according to the study of Natsiavas and Paraskevopoulos. The constraint equations between the vehicle and auxiliary contact bodies, for example, includes the motion constraint between the two subsystems and its derivatives in time. These are accordingly multiplied with mass damping and stiffness constraint coefficients. Similarly for the constraint equation between the bodies and the bridge. So eventually, the entire system can be described with a set of equations that include the equations of motion of the vehicle and the bridge, the equation of motion of the auxiliary contact bodies, and the constraint equations between the two subsystems. This system of equations constitutes the proposed dynamic partitioning method. The proposed method solves the vehicle and bridge systems separately, which means that the system matrices do not change in time. This is opposite to classic coupled approaches, which in some cases result in time-dependent system matrices. In this way, we can decrease the computational effort, as will also be demonstrated in the numerical applications later. In addition, the system of equations includes exclusively second-order ordinary differential equations, which avoid the numerical drifts and instabilities of differential algebraic equations. In this way, since the vehicle and bridge systems are treated separately, they can either be solved in parallel, which can additionally decrease the computational cost of the analysis, or can also be solved sequentially. So now, in order to demonstrate the accuracy and efficiency of the proposed dynamic partitioning method compared to other approaches, I will present two systems, a simple consisting of a single vehicle and a singly supported bridge, and a more complicated model consisting of an arch bridge. So the first system, as I told you, consists of a simply supported bridge traversed by a single vehicle. The dynamic partitioning method, which is shown here with gray line, is in perfect agreement with the benchmark solution of the unconstrained system, shown here with black circles. Remember that the term unconstrained system corresponds to the constrained mechanical system after substituting the involved kinematic constraints. On the other hand, solving the system with index 1 differential algebraic equations and without applying any stabilization techniques leads to numerical instabilities as soon as the vehicle enters the bridge. This is attributed to the local violation of the constraints, which creates numerical errors which are transferred throughout the time integration. Then the numerical instabilities of the differential algebraic equations become more evident when considering more involved vehicle bridge systems, as for example, a 10-vehicle train traversing an arch bridge. Once again, the proposed dynamic partitioning method is in excellent agreement with the benchmark unconstrained system solution. On the other hand, the differential algebraic equation solutions show some instabilities when no appropriate stabilization technique is applied. Specifically, the unstabilized index 1 differential algebraic equation solution leads to numerical instabilities as soon as the vehicle enters the bridge. Then, an index 3 differential algebraic equation solution leads to instabilities of purely numerical nature to the bridge acceleration and the contact force of the vehicle. Importantly, the dynamic partitioning method also decreases the computational cost of the analysis. Compared to a coupled index 1 DAE solution, the proposed algorithm is 8.8 to 10.7 times faster. This is attributed to the fact that this method, the index 1 differential algebraic equation method, eliminates the Lagrange multipliers, so it leads to time-dependent system matrices, as opposed to the dynamic partitioning method. Then the solution of the unconstrained system also leads to time-dependent system matrices, but solves for the minimum number of degrees of freedom, and this is why the time-cost ratio appears to be slightly smaller. Still, the dynamic partitioning method is faster. Then, solving for an index 3 system of differential algebraic equations, we see that the dynamic partitioning method is still computationally more efficient. Thus, compared to existing numerical algorithms to solve the VBI problem, the proposed approach is both accurate and efficient. So I will close this presentation with some main features of the dynamic partitioning method. First of all, the proposed partitioning method treats the vehicle-bridge interaction problem both accurately and efficiently. This is achieved by introducing auxiliary contact bodies between the vehicle and the bridge, which allows the separate treatment of the two subsystems, which can significantly decrease the computational efficiency of the analysis. Then, by assigning dynamic Lagrange multipliers, it allows the formulation of both equations of motion and constraint equations as solely second-order ordinary differential equations. This formulation avoids numerical drifts and instabilities, which are typically associated with differential algebraic equations.